This video is on estimating the noise variance. Thus far, we've assumed that the noise variance sigma squared is known. However, we can use the principle of maximum likelihood estimation to obtain a maximum likelihood estimator for that noise variance. We use the principle of maximum likelihood estimation to obtain the maximum likelihood estimator for the noise variance. We follow the standard procedure. We write down the log likelihood, we compute its derivative with respect to sigma squared, set it equal to 0, and then solve. The log likelihood is given by log of the probability of y given x and theta with variance sigma squared, and that's equal to the log of the normal distribution of y given phi transpose of x times theta with variance sigma squared. That's equal to the sum of negative 1/2 log 2 pi minus 1/2 log sigma squared minus 1/2 sigma squared yn minus phi transpose of x times theta squared. Cleaning that up, we get negative n/2 log sigma squared minus 1/2 sigma squared, the sum of yn minus phi transpose of xn times theta squared plus a constant. The partial derivative of the log likelihood with respect to sigma square is given by p of log p of y given x and theta with variance sigma squared divided by the partial of sigma squared. And that's equal to negative n/2 sigma squared plus 1/2 sigma to the 4th times s, where s was defined on the previous slide. We set that equal to 0, and if that's equal to 0, n/2 sigma squared must equal s/2 sigma to the 4th. If we solve that, canceling out the 2's, multiplying both sides by sigma to the 4th, and dividing both sides by n, we get sigma squared equals s/n, which is equal to 1/n times the sum of yn minus phi transpose of xn times theta squared. Therefore, the maximum likelihood estimate of the noise variance is the empirical mean of the squared distances between the noise-free function values phi transpose of xn times theta and the corresponding noisy observations yn at inputs xn. In our next video, we'll talk a little bit more about this in the context of overfitting.